So our next topic is a consideration of the balance of linear momentum. It's extremely important equation for us that will lead us to the equilibrium equation. Essentially, that is the differential equation that we are solving for in the frame of solid mechanics. Now, so we basically start from the very well known for you physical law of so just formulate that was formulated point-wise or a mass point assumptions as when they have this mass point whatever it is. So to change the linear momentum, that mass point, according to Newton's law, you need to apply force. That basically is the driving factor or the source for the change of the linear momentum. And so more precisely here, right? So this mv is our is m is the mass and v is the velocity, and the multiplication, the product, it basically gives us the linear momentum here, right? And again, so the force, this is the resultant force of can be many forces that act on that mass point, and the resultant we'll call F, and so that will change our linear momentum. Now we don't like we don't like working with mass point because, well, we actually need to extend this to the continuum. We have a body and each point can deform, they are connected, and we are not dealing with a discrete system of mass of different points. So we need to generalize that to the continuum, and therefore we reformulate that to the Newton's law, to what is also called sometimes Euler's law, or the linear momentum for continuum. And basically what we did here was said, okay, we're still looking into the change, this d dt of some measure similar to what we have here, right? So this is our linear momentum, and now so we're saying, so we have this linear momentum at each point, right? So when we integrate rho v, we take the density of that, okay, so that some small element around some point and multiplied by the value of the velocity at that point. So then that will be our linear momentum, and then we can calculate that linear momentum of any volume, any body, just that we specify this integration. So that's basically our linear momentum here of the of a continuum body, right? So that, say for example, that potato that we deform from this initial to the current configuration. Now then we have this second part. So there is this force which we called resultant force. But then that leads us to a little bit problematic formulation of what's going on here, because now if that's a force that is supposed to be applied somewhere, right? So what is this force resultant? When it was just one point, that mass point hypothesis, it was using Newton's law, so it was very clear what it is. So just it applied at that point exactly. So now in the continuum we we can have forces that are actually applied at different points, if you like, or maybe they distributed differently along the surfaces. And there are in fact actually two types of forces that we can distinguish. Some that will be applied as a so-called let's say they can be applied on the surface, right, as typically we would push or pull the material at certain points that continuum body. But there are also a second type of the force that we actually very familiar with, and for example that would be the gravity, or as an example of so-called body forces, which is applied to the volume element of that. And so as a result, we roughly divide that resultant force into two parts. So there will be a first part, which we'll call body forces, and so the second part is coming with as tractions. So and the body forces here, that B, we denote the body forces, and so you can notice that here we actually perform the integration over the volume, right? So that's defined as force per unit volume, while T, what we call traction, right? That is so the force per unit of area. And so again, so here we measuring this in the current configuration, right? So this is surface integral, so the forces that acting on the surface, right? And we do all the integration over the surface that enclose that volume, and all the body forces we integrate that act on that volume. We integrate them obviously over the volume. And again, this is so example for that can be gravity. That is a perfect example of that. So that for rigid materials, okay, gravity probably is is not as important in many cases, not always, when we talk about deforming rigid material, but actually soft materials can undergo deformation extremely often, like gels, just under the action of gravity, right? So there are other examples of body forces, for example, as in magnetic, if the material is magnetically inactive and have, for example, some magnetically active, have some particles that can be magnetized within the material, we apply external magnetic field that also will exert forces of actually different specific directions that would be different in nature if we compare them to gravity. Or there are also electrostatic forces that also can be induced in a polarized material. This is just examples. So for that, again, so there are examples, physical examples of body forces, and again, so the most important probably for us at this point, that would be gravity, right? Okay, but bottom line, so the two type of forces that that we split our resultant force, and so in that way we actually can formulate what the force is and where it's applied. So it would anymore we have we don't have anymore the problem with this concentrated force that was applied at some point, and so this is the source for our change. So that's on the here on the right hand side of the equation. This is the acting forces, the source for the change of the momentum. If it changes, so the linear momentum, so there are non-zero something on the right hand side that leads to the change in the linear momentum described on the left hand side. Now with that, what we would like to do next, so once we formulated this in an integral form, this linear momentum balance, similar to what we did to the mass conservation law, we would like to localize this formulation and actually write it locally without the integrals. But the problem here arises immediately that we have two types of integrals here. So we have the volumetric integrals, so that comes here with the dv and dv here, right? And on the other hand, we also have this surface integral, is the integration over the of the area that encloses the volume. And so that is what we will try to deal next and try to localize that. So first, just to expand what we write on the left hand side of 3.7 of the integral form of the balance of linear momentum. So Okay, so again, so we just rewrote what we had on the, so that's still our linear momentum here, a change in linear momentum, so that we take the material time derivative. And so now we are going to use that formula, so that similar formula when we have the integral, and we take the integral in the current configuration of the current volume. And so you remember before that we had that function psi here, and so we integrated, and we saw that in addition to the to that function right here, we have also additional term that function was multiplied by divergence v. That it comes that from the rate of change in the volume, right? And so here, okay, so we can just imagine that instead of that function that was psi, right? So we just wrote now v rho, and basically all the derivation would work exactly the same. So this is a generic formula that we can use for the taking the material time derivative of the integral in the current configuration. And so we have these two terms here, and now we also remember that this left hand side, right, is driven by the forces, right, by body forces and attraction that applied there. And so this is just copying the previous formula for our linear momentum balance. And now we can, instead of that what we have here on the left hand side, we can substitute the this part in here, and just instead of this expression, well, because this is in general true, of course. And then in addition to that, we also can, so what we're trying to do is trying to combine all the forces, all the terms that are having that integration over the volume. So basically we're going to take this part and basically just pull it, combine it with what we come from here, and then we just will rename our body forces and write it in a more compact form, when everything that went into under that volume integration, right, over the volume. So all of that we'll call the generalized body forces. And what we had in there, we had obviously that B, that body forces, the body forces as we know them, with minus, and we also had all of this, the d v rho dt plus v rho divergence v. So we can basically just define it again. So you can see, so we just redefine the body forces as those that appear as terms under the where we have the integration over the volume. So there is a body force actually here, and if we continue that blue line from here, these two terms exactly coming and contributing into these two terms that we just obtained again, coming out of the taking the derivative of material time derivative of the integral and the current configuration. So now ideally at this point we can say, okay, we're almost there. So whatever is under the volume integral, so we should be able at a certain point to say that, okay, so that must hold true anyway, regardless of our choice of the volume where we want to integrate. And the only problem is still remains here with the with this surface integration of the traction forces that we applied on the surface. So if we find a way somehow to convert that into the volume integral, then we'll be able to transform that free 9 into the we would be able to pull everything under the integration over the volume, and so then we can localize that and write the equation without the integration. So that will be our next order of business, to actually try to see what is how we can do that, how we can convert that integral into the volume integral. And as we'll be doing so, we'll introduce quite important and fundamental things that will be useful for us. So, and so, and our detour starts from the so-called Cauchy assumption. Now, let's introduce it in the following way. So we have our body, right, and then we can imagine just a cross section here, right? We have a cross section, some arbitrary point, and that cross section is defined by the normal n. So that normal n defines this cross section, this orientation. Now, then, what we are going to do, we are going to try to consider what's going on. What is this traction vector t? What it is at a point, right? So, and to that end, we identify some small area element on which we can identify the resultant force that is acting on that area. And again, so you can imagine that there can be any combination of forces that we applied on the body, and as a result of that, there will be forces, at maybe zero, maybe non-zero forces in different directions that can be identified at different points. Now, so here we're looking at some particular points, and at that cross section, again, not arbitrary cross section, but of course any cross section is identified with its normal vector n, and so then we find this small area element, and so what we're going to do, we are going to actually to make it as small as possible. So we're taking the limit of this area going to 0, and we calculate the quantity of this ratio of that resultant force of all the forces that act on that small element, at that point, and so which will be delta t, and we divide it by the area. Right, so basically, in that way we introduce this traction vector, right? So in a way, this traction vector is may look a little somewhat familiar to the stress, to the definition of stress, where we took some forces and divided it by an area, but okay, we kind of jumping ahead of ourselves. So yes, we said at one point that stresses is a second order tensor, and this is this t, this traction is still just a vector, so first order tensor, so that cannot be exactly that. Also, as you can see, somewhat connected, and we will establish this connection, obviously. And so, and what we are saying here now is that so the assumption, the Cauchy assumption, is that this this traction vector t depends, well, obviously depends on the position, right, when the point where we measure, but also on the cross section itself. So depending on how we divided that potato, right? So that body, at which angle, for example, we pass the cross section. So because it can coincide, it can be at some angle, it can be perpendicular to the force at that point, and so that will change the traction. All right, so this is this may still look a little bit abstract, also okay, quite an intuitive way to measure, to relate forces with an area and head towards the stresses. Now there are important consequences of that we can deduce, and that will we'll try to use in our derivation of this linear momentum balance. So the first one that we are going to deal with that is called the principle of action and counteraction. So now we are going to look into into the magnitudes of the forces that each part of that divided potato of that body exerts on each other, and so maybe we can divide that something meaningful for us. Now remember that this is our Euler law when we so there is something complicated here in that BG, in this generalized body forces. It doesn't matter, so this still we know what it is, and so this is the way that's that can be applied to any body or any part of the body, right? So and so that we're going to use that very explicitly after we taking the body, and then we split this body into two parts, right? And so there is a surface that will separate that, right? So this is schematics of this. So we had the whole body here, and then we came here with that area and separated it. So of course it's kind of sketched in 2D, but you can imagine that extending that into 3D. And then what we can do, we can actually say, okay, so this Euler's law applies for the first body, for the first part of that. So that right. So we can consider this part, right? There will be traction that are applied on this on the area, on the our usual area A1, plus that area that is separating that from another body, from the second part, from the which is denoted by V2. On the other hand, we can also write these equations for the second volume, right, for this second part, and basically again here we will be integrating over over that volume V2, but then our area here will be this part A2 plus the area A star. So when we will going to integrate all the tractions here, and so but still the same formula will apply. So we can write first for the volume for the part of V1. So we just okay, so our integration here, so the I will denote that by dV1, right? So this is the part. Okay, let's denote this. The blue one will go here, right? So when we integrate this part, and the green one is showing here, right? So the same, all the body forces that we are going to integrate over V1, and they need to be equal to the traction that we collect as we summarize or integrate over A1 of the outer surface, and also to, on these all the traction that acts here on the as we go over the areas that this surface that cuts these two parts of the same body. And so here it's important for us to know that we actually have the normal here, right? So that defines as A star. Once that we come to the integration over, so for when we integrate over V1, so our normal is this one, so this is the outer normal. And when we go to integrate over this area A star, we consider in V2, the outer area will be exactly minus n, right? So and I will yeah, and so that's therefore I will circle this in blue so that it corresponds to our integration here. So and hence here our the normal is minus n, right? So when we integrate it in here. Okay, so however, we also can say that well, the obviously when we integrate, so as all the body forces over the volume V1 and then V2, the sum of this will still be equal to the total integration over all the same body forces over the whole volume dV. So I can just say, okay, now I take this plus that. I probably should use a different color for that, so it will not be associated with any of that. So this plus that will be just the integral of bg over dv, the whole thing. And now with the so the same thing also for these parts as well. So this will be just okay, produce the integral of bg over dv, and this will produce the same similar manner the integral of t over dA, right? So just okay, sum of both of these is the same. And this is good. So we kind of recover a part of this free 9, but we get the additional terms that come from this integration of the surface on that surface that separates these two. So okay, let's look into that. So we basically have, right? We basically have that that so we have this part that this is exactly that free 9, and we have what appeared here, the traction that we integrated over the same area dA, but with different normals. And so this whole thing, okay, so it just we can get rid of that, because while that if we pull it on the left, so that will be just 0, right, by the nature of 3.9, right? So then we just have to request that this part here is also 0, and so then then eventually we are just going to look into that and say, okay, hey, that must hold true for any for any area or any that we wanted to cut it with. And so the only way how we can ensure that is that whatever is inside this integral is 0. So we need to say that the traction on the one side is compensated by the traction outside. So you exert force on the opposite side, and that same force is exerted on you by the by the other part of the body, just with the opposite direction. So that is, and that what we call is action and counteraction principle, or also third Newton law. Right. So again, so this conclusion is the that will work in any point, right? So this is the just what we call it again, localized. It's a localized form of this, right, of that integral form free for t. All right, so we established that, and so now we're going to the second conclusion, consequences that we can draw from the Cauchy's theorem. And so we're going to look into the so-called Cauchy tetrahedron, and I'm pretty sure that you've seen at least a 2D version of that, in a simplified version connecting attraction and stresses in the mechanics of materials. So that would probably look like, let me sketch it here. So might look something like that when you have a two-dimensional system, and you consider this like that, and so there was some normal and some resultant forces. Okay, so but this is, again, this is not new, so that's why I'm not putting much effort to to sketch it nicely, right? So that is in 2D, and then you were able to connect that the stresses that would compensate, so that would work on in these directions, with the connect to the forces that can be that you can calculate based on the normal here, and of course the normal changes with an angle here. In a similar manner, we're going to use this Cauchy tetrahedron to obtain to illustrate, let's say, not very usefully, to show the relations between stresses and traction, so-called Cauchy theorem. Okay, so okay, let's see what do we have here. So we have here this tetrahedron, and so we have so the arbitrary, so it's built on our coordinate system. Let's put in the center here. So there are vectors E1, E2, and E3. So this is standard, and so then this tetrahedron is built by drawing this. Okay, so having this plane at some arbitrary angle, and so basically didn't specify what is the coordinates, this y1, y2, and y3, so it can be anything. But so of course, depending on our choice of this y1, y2, and y3, so there will be different normal vector, and again, this is a unit vector for our so to put it conveniently, so that basically specifies how we put this area, the triangle here in this to build this Cauchy tetrahedron. So then we denote this the area of that guy CDB. So the area of this is some known area that we can calculate if you like, and so let's call it A, and then all of the other areas can be calculated as projections once we know the components of the normal n. So basically, for example, COB will be calculated from the area A. Okay, let me just denote this COB here, right? So the projection is this blue area here, right? Okay, I hope I'm not making this even miss here. So that COB is a projection of that element area CDB, and with the component, so the component N1 that multiplies this projection that makes it on the area COB. And and basically it works the same logic here. So if we want to calculate COD, so that so the opposite normal component into direction 2 will be the factor, and DOB here the component of in direction 3 will be the factor that will project our area on that new area. Okay. So, well, this is a simple geometrical concentration that we're not really going too much in depth here, but they're important for us because basically now we are going to write our equations, right? So the for the linear change in the linear momentum, right? So we know that the generalized body forces that volume integral changes on account of the surface our surface surface integral of tractions, right? And so then we can write we can actually what we have here and that's where the simplicity of this geometrical volume of the tetrahedron helps us, because we have basically only 4 faces, right? The one that is defined by the normal, and these that are built on the on the planes on the planes that are built by the our coordinate system, right? And so we have 4 terms here. If we want to integrate over the surface of that Cauchy tetrahedron, we'll have 4 terms. So on the left hand side we still have our body forces, and then on the right hand side, so we have the integral over CdB, so on this on this area, so that's where the traction is. And now so we also have the traction over this the area in the direction E1, so but this is the opposite direction. So when we consider that COB, so the outside of the screen there is a normal to that is in the direction of E1, but in the opposite direction, so this is minus E1 from here. In a similar manner, when we consider COD, so the normal to that, the outer normal, will be in the opposite direction of E2, right? So that's here, and for this lower face DOB, so the will go into the opposite direction here. So the normal here will be minus E3, right? So on this that will be minus E2, the normal, right? And on that side that will be minus E1. Okay? Okay, so basically we have this traction, right? And so now we need to integrate this, and so what we're going to do here, we're going to use what is called mean value theorem, when we basically can convert our integral of the volume over the surface into the basically multiplication of the the mean or average value over that volume or over that surface, multiplied by the area by that volume. So another useful tool for our integration magic box, right? And so we're using that mean value theorem, and basically we're saying, okay, so the average of that here of these body forces, generalized body forces, is here, and it is multiplied by the volume, and the volume is obviously nothing but basically this h, the height here. Okay, so the dashed line here, that the that can be also calculated based on geometrical consideration. So once we specify how we draw this cross section to build our tetrahedron, so basically based on n or coordinates y1, y2, and y3. So we have the height, and we multiply it by the area A, right? And that will give us the volume with the factor of 1/3. So for the tetrahedron, right? So the area that is denoted in red multiplied by the h, and so factor 1/3 will give us the volume. So this is the volume, right, of that tetrahedron. Now, so for the first part from here, again, we basically use the average value of t acting here on and multiplied by the area A. So because this is basically CDB, so in COB the area will be A multiplied by n. So this is the weight h. This is the area here, obviously. So we will calculate that, and in a similar manner for COD, the area will be an1 and n2, and then here the integration, so the area will be an3, and so these are the average values of the of the traction. Now, okay, so let's just look into this 318 a little bit, and as you already probably can expect at this point, is that at certain point we will say, okay, we can make this tetrahedron a very, very small element, our usual trick, right? So how do we do that? We just say h becomes very, very small. Okay, so all right, so h becomes very small, everything shrinks. As h shrinks, then the volume shrinks and the area also shrinks. So now let's see. Okay, so let's just clear for us a new slide, right? Copy this 318 right here. And so basically what we're saying is that, okay, we're demanding that h becoming very, very small. And so then we can notice that, in fact, okay, yes, we know that with h, a will shrink. So a will also be always here. But the thing is that we actually can get rid of a right here, right? So there's that because that's appear on the right and left hand side, and so we can get rid of these a's, and then we will see that while the left hand side depends on h, so right, so that becomes a very small number very fast as h approaches 0. Then however, the terms that came from the surface integration are not effective with that. And so basically when we say, okay, let's consider a very small tiny tetrahedron with the limit h going to 0, that will basically help us to eliminate this part. And so, and then we can say, okay, so this sum of these forces that appear here, so will be 0 for very small, tiny element. So basically, you can see that what happens on that tetrahedron. So we have that the traction that acts on the surface that we cut at some random random angle that is defined by that normal n is equilibrated by the other traction that appears on other faces, right? So we have 3 other faces that need to equilibrate that t here. So we actually can rewrite them a little bit differently in the following way. So first of all, we just can take all of them, all these that are opposing, and either pull it to the left hand side or just pull this Tn on the right hand side, on the left hand side, and then it will become with minus, so minus is not good, so we'll just multiply everything with -1 as usual, and then we'll obtain that with a small trick in between, so that we can actually express the components, right, as a projection, as a projection on the corresponding basis vector, right? So n1 will be the projection with e1, n2 with e2, and n3 with e3, and so then that's basically what we exactly have here. And again, so that only serve us to express that t, right, that traction vector, and remember we said that it depends on that, on how we and how we how we actually determine our cross section, that area of that helps us to build a tetrahedron. So another thing that we can notice here is that we actually have that can pull that n outside here, and right, and so we can rewrite it a little bit differently in this way. So n is going outside, so that's exactly here on the right hand side, and then you can see that there's some sort of transformation in a very important manner, is that you can see this some kind of components, right, of what is more familiar for you to see as the Cauchy as a stress component, right? So this is, again, so you see this vector, this is also vector, so it's tensor product, so we elevated that into second order tensor, and okay, so of course when multiplied with dot n, right, from the right here, so that will reduce still to the first order tensor or vector traction t here. But you can think again, connected to the example of how the stress was introduced in a more basic course on the mechanics of materials, when you had this force or traction acting on certain phase, that is in this the direction of that phase on which text is defined by these vectors e1, e2, and e3, and so that is giving this relation. Or simply put it, so here is our super important formula. 320 is relating this traction to the stress through the normal. So the so, and very importantly here is that while the traction vector depends on how we decide to put this normal, at which angle, for example, right? And again, in two-dimensional case that you've seen, so there could be different angle would determine that n differently, and then your traction vector on that surface would change, would be dependent on t, on n. However, that sigma, this stress tensor, or what we call Cauchy stress, is independent of our choice of that n, and that basically defines what is called a state of stress at a point. So it's uniquely defined by this measure, by this second order tensor Cauchy stress. All right, so at this point, so we'll just continue our detour of introducing Cauchy stress, but then right after that, after we looked into this and defined the Cauchy stress, which is through this very important formula 320, so we'll get back to our derivation of the linear momentum balance. And so let's look a little bit more into this Cauchy stress tensor and see how we can so how it looks like, and just just an illustration of that usual cube of and different components of the Cauchy tensor. Okay, so so here is our given our typical exercise that we're going to do, right? So that's we have a second order tensor sigma, and so if we want to write this the components of sigma, right? So this sigma ij, so these are scalars, so they're indexes. So basically what we're doing, we are calculating the projection of that second order tensor on this dyadic product of this eij basis vectors, and so then we can calculate that, right? So by substituting this traction like quantities and using our double dot contraction to pair this certain to just ensure the order of multiplication with the dot product here. So right, so that our double dot would mean that well, actually this one will be paired with this one, while this one second will be paired with this one. And that's exactly what we rewrite here in the next line. And so and from EJES multiplication dot product, we obtain the delta JS, and so luckily for us it's also we can find where that S repeats itself, and so we remember that the action of delta is such that we can rewrite it in so we can just substitute the indexes and get so that S just replaced by the second index of Kronecker delta, and so then you can see that the illustration of that would be okay. So let's say we have this so we're looking at the cross section at the face that is defined by E2. So this is the normal here. This is some traction, the resultant traction on that surface, that element, and basically we have now a few components of that of that tensor, right? That is calculated on the surface that is defined by E2, right? So this in this plane. And so the components of that will be the component will be written like that again. So we can show this the vector, that traction vector can be the components of that traction vector will be built by this the corresponding components of sigma to 2, and they basically obtained obviously by the dot product of that t traction vector acting on that face that is defined by E2 normal. So this is a normal for that defines its face, and so there is some that traction that, let's say, looks like that. And so basically in the case when all the components are non-zero, and so and then to obtain these components, you basically have for example for free 2 you would multiply it with the E3, right? So the dot product to E3. So basically exactly what is written here is just for each component for 1, 2 you multiply it with E1, so that the projection of T onto this direction, and then for 2, 2 is the multiplier is E2, so basically projection that T onto this direction, and then for the 3, 2, so you you project that vector t onto this direction, and basically that from traction on each face you have these three components. And so again, you can recall this discussion that so this component, the part that coincides with that, or the projection of that, leads to tension or compression, tensile or normal stresses, right? But for example, these two that act on the surface, on the face, within the place of Earth, so they are these are typically called shearing, right? Shearing components. So this will be shear stress, right? When this will be E2 sigma to 2 will be the normal stress. And of course, this can be also identified on each of these faces, right? And so so the normal stress is sigma 1,1, sigma 3,3, and sigma 2,2. So these are contributing to compression or tension, right? And all these that are acting on the face within the plane of the face. So these are shearing stresses, right? So this is but this is of course a repetition of things that were discussed previously. So now we'll just what we'll do, we'll just give a very quick example of just some random numbers that we are going to illustrate that again the state of stress it can be related to the calculation of traction on a surface, but then you really need to give this traction and this surface and to specify that by the normal, and then you will see obviously that the traction actually will be will depend not only what this point feels, but also will depend on how you at each angle, for example, you come and cut this cross section. So okay, so here's a quick example. If you like, you can practice that, calculate that yourself. So just pause this video and calculate before go. So let's just state the problem is, and so so we given the state of stress. So somebody came and say that our stress tensor is such that so we have 1, 2, 3, 4, 5 components. And okay, so there are no dimensions, but of course, obviously the stresses measured in Pascal on Newton per meter square, so directly comes from definition of that. So maybe megapascal or gigapascal, so that dimensions of 1 Newton per meter square. Okay, so that's at mega. That I will need to multiply with 10 to the power of 6 here if that mega. Okay, so mega was not necessarily here. Anyway, so so we have this given state of stress. So we have 5 components of the stress that are non-zero, and so then we're given the surface that is defined by this normal. So they just okay, this vector that has all the components here, and so what we want to do, so what we are required to do here is that we want to calculate the normal component to that surface of the traction. So we're going to calculate the traction. So basically the question is what is the T, but more precisely I would ask what is the and also would ask what is the normal component of the, because T can be split into normal and tangent components, right? So let's call it TT, right? These that are normal to that surface that's defined by n, and these that are actually lie on within that surface. And so and so the question is what is the traction and what is the normal and what is the tangent components of this. So and obviously what we are going to do here, we just simply use our Cauchy theorem that says, okay, so the traction is nothing but the multiplication of sigma by n, the dot product, right? So basically what we are coming here with, we come with, so we write the sigma, right, and multiply it with n from the right, so we, to make it, so if we want to make it t, so if we want to make it t, so we multiply it with the n from the right, so basically I come in here and multiply with dot product with n, right? So I came here and multiplied from the from the right with n, and basically I introduce that n everywhere, and now I just need to substitute that that n at each of these components and see what I'm getting here, right? So that is so that n is I'm coming here with that n, and I need to see which result is obtained here. All right, let's just try to get this right. Okay, so the first one that will be non-zero is the one that we take that, okay, so 7e1, right, that will remain, and so the one that is dot product will be non-zero, that will be multiplication of this e1 with e1 here, right? So that will be non-zero. The rest of them they're perpendicular, so the projection is 0. So this 2/3 of that, so from the first term. So then in the second term, so we multiply here e3, right, this e3, that's right here, with n, and so we have only so we have 1/3 of that, of e3, so we have minus 2/3 e3, oh, e1 still, right? So that still e1 here preserves. So then so we come here, so there is e2 multiplied with n. The only thing that will remain, okay, so this plus 5 e2, this is e2 multiplied by e2 multiplied by n, so that will be minus 2/3 of that, and and so then we continue this this minus 2e3, and then we need to multiply e1 with n again, and but we know that this already we had here, so we had 2/3 here again as a result of this multiplication of e1 with n. So right, so there's only 2/3 here that comes out, and then the final the fifth term is 4e3. Right, so now we multiply e3 with n, and so when with n we only have this 1/3 here. Okay. All right, so we can now do the very quick summation here, or analysis, and so actually we immediately can see that there is 4/3 e3 here, and there 2 by 2 also with opposite sign of e3, so 4/3 with minus, and there is 4/3 of e3 with plus, so we get rid of that. So with e1 we had 7 of these that were 2/3, so minus 1 of this, so we have 6 of these 2/3, or so eventually we have 4e1, right? So from these two we obtain 4e1, right? And if everything is correct, so we have this also only one thing that comes from e2, and that actually will be minus 10/3 of e2. So basically we calculated the traction here. So so the traction, again, more nicely written form is in 4e1 minus 10 thirds of e2. Okay, so this is just an exercise, of course. So just some sort of random numbers that were given as a state of stress. But you can see that basically the state of stress is it's basically defining the physically what the point feels in terms of how much it's compressed, sheared, or everything that acts on that. So the traction the traction vector actually doesn't really so it's not independent of our choice of the normal. So it can change. So so we can change the normal, go in one angle or another. It will change, right? The result that we obtain. So obviously, if we multiply that with something else, so the result will be different. Now, okay, so let's calculate the normal component, and the normal component is basically we just need to take this result of t and multiply it with n. So just project it to n, right? And and so then we that would give us the the magnitude of that if we calculate the projection multiplying with dot vector n. But if we want to make it a vector again, so we multiply it with the unit vector n. So the normal component will be, okay, so that basically again, so this is the projection of that t on n, so the component in the n direction, and then so which is a scalar, basically the component of that, and then we multiply it by the n and making it back a unit vector, multiplying by the unit vector, so effectively making this again a vector of a certain magnitude, that is the projection of t in the same direction. And so what we're doing then is just we're taking that, okay, so basically substituting that t in here. So first to multiply it with n again, so we basically take that traction vector t right here, multiply with n, so we need to do the whole thing again and again. Okay, so first to multiply the first component of 4e1 with n, and here we see that what we will have is so that will give us 8 third of 8 third, right? So basically that's exactly what so e1 multiplied e1, so the others don't contribute because they're 0, and so the second part will be minus 10 third. So now we need to find the one that is non-zero for e2, so that's component multiplied with minus 2 thirds, so making it plus, and so we're having here 24. So okay, so that will be 24 over 9, right? So this part, right, and this is plus 20 over 9, and so we have 20 plus 24 over 9. We have so the whole thing will be just the number 44 over 9 divided by 9, and so this is multiplied by n. Right, so so we have that 44 over n, and basically we're just going with this number back and multiplying that, substituting between instead of n the value of given n, and so then 2 thirds multiplied by 44 divided by 9 will be, okay, obviously 88 divided by 27, and the same with minus 2 over 3, and here 1 over third. So so we still have that same 44, but we have 1/3 here, so making that 9 going in 27. So again, so it's useful to make these calculations. And now, so to calculate the tangent component, so obviously we don't want, we're not going to convert n normal into the its perpendicular counterpart. We just use yep. Right. So that probably will be the last thing that we are going to do in this particular video lecture. And so we just take this this formula, rearrange it, because we are after the tangent component of the normal. So we just write t. The tangent is nothing but the original direction minus Tn, and so then so we can write it in this way. So so basically we're substituting so we're substituting this instead of t, right? And then we're substituting what we obtained for the normal component here, right? We're substituting that exactly here. And so if we do this correctly, so the tangent component will be this. Once again, so this is just a little bit of illustration of how this machinery works. Of course, the numbers that we were given in the beginning, they're rather random, can be anything, just showing you that the, again, illustration of how that stresses and the traction calculated if you have some numbers with you. So because before that we had this in a very just in a rather abstract and form. So this is supposed to provide you some illustration of how these multiplications work, and also emphasize the point that actually the stress does define the physical state of that point, the so-called state of stress, while the traction is still something that is to define properly. You do need to specify at which surface you calculate the traction, while the stresses don't require that. All right, so that will be all for now. So, and then we'll continue with this to derive our localized form of the linear momentum balance. See you then.